Hello, this is MAT 221. This is Mrs. Johnson. This is more examples dealing with section 4.1, which is on related rates. This particular PowerPoint accompanies the worksheet that is in the worksheets folder for section 4.1 and has notes and examples on it. So let's begin. We've been taking derivatives with respect to x for most of the entire semester. We even took derivatives implicitly, but as a function of x. Suppose a particle is moving along the curve y equals x squared, the parabola, and as it moves, the x and y coordinates are changing at the same time. If we viewed their change as a function of time instead of y as a function of x, but as each piece as a function of time, then we could represent the rate of change in the y values with respect to time as dy dt, and the rate of change in the x values with respect to time as dx dt. So if we find these derivatives in the same way that we found derivatives implicitly, let's look at how we would do this. Here's example 1. Suppose both x and y in this case are functions of t. Differentiate this expression y equals x squared with respect to time, or with respect to t. If we wanted to solve for dy dt, what other information would have to be given to us in order to solve the expression? So if we're starting with y equals x squared, and we're taking the derivative of that expression with respect to t, implicitly doing the derivative here. Remember, the variables are not matching on either side here, so we have to use the chain rule in each case. On the left side of the equation, we get dy dt. On the right side of the equation, we take the chain rule and we say the 2 comes to the front, leaving the inside function, subtracting 1 from the exponent, and then taking the derivative of the inside function with respect to time. And because in this case neither variable matches the t, we bring in that Leibniz expression for the derivative. Now let's answer the second part of the question. It says, if I wanted to solve for dy dt, in other words, if I wanted to know what this quantity was, what other information would I have to be given? Well, I'd have to know the value of x, and I'd have to know the value of dx dt in order to get a value for dy dt. All right. So let's look at example 2 that says, suppose we're moving along this a particle is moving along this same curve y equals x squared, and it is moving horizontally at 2 centimeters per second. Find the rate of change in the particle's vertical position at the exact moment that the particle is at the point 39. So this is in a concept similar to what we would study in physics, in that the particle is moving along this parabolic path. And we know in this case, its horizontal speed, or its movement in the horizontal direction, and how fast it's doing that. And we also know at what exact point we want to look at what's happening in the situation at the point 39. So we're going to start with what we ended with. We said we could find the derivative of this expression with respect to time. But now we know the values for x, and we know the values for dx dt. We know in this case that the value of x is 3, and the value of dx dt. Now why do I know that's dx dt? Because it says this is how it is moving in the horizontal direction. And remember, x is when we're moving horizontally on the Cartesian plane. So in this case, x equals 3, and dx dt is equal to 2 centimeters per second. Notice also I knew this was a related rates problem because of the fact that I'm given a rate of change and I'm given some other information here. So now I can plug in those values into the expression and then I can solve for dy dt. dy dt is equal to 2 times 3 times 2 centimeters per second, which gives me 12 centimeters per second. This tells me that the particle's vertical position, or in other words, its change in y, its change in its vertical position, at this exact moment, it is moving at 12 centimeters per second. So in related rates problems, you'll have an equation relating two or more things that change over time. And we want to find the rate of change or a derivative of one of these things. It's important to understand that without some conditions being given, we can't solve these problems. So here are some guidelines we'll go through. And these problems can get tough because we have to set the problem up from the word problem. Step 1, read the problem. Really, you'd be amazed at how many people skip this step and then read it again to try to find the information. Step 2, if you can, draw a diagram showing what's going on in the situation. Identify all the relevant information and assign variables to what is changing. Use the general case that numbers should be used for values that never change in this situation, and variables for anything that is going to change, even if I have information about that quantity at a given point in time. If that quantity is changing, I have to use a variable for that quantity. Related rates usually involve motion, and any diagram you draw is like a still picture of what is occurring. Any part of your picture that never changes can be labeled with a constant or a number, but any part of a picture that is in motion or is changing must be labeled with a variable. In other words, if a radius of a circle is increasing and you're asked to find the rate of change in the area at the exact moment when the radius is 5 centimeters, then your diagram would be a circle, of course, but you would not label the radius 5 because the radius is changing. You would label the radius with a variable r. Step 3 of this procedure would be find an equation that gives the relationship between the variables that you just named in step 2. This is sometimes the hardest part of related rates, coming up with an equation, but for the most part, the problems fall into 3 categories. A triangle that we can use a trigonometric ratio involving the sides and angles, the Pythagorean theorem, which is involving the 3 sides of the triangle, or a known formula like area or volume or distance. And you don't have to memorize those formulas. We'll always be able to look them up or have a reference guide to give us those formulas. Step 4, find the particular information, the values of variables at the exact moment you drew your diagram for the problem, and write them down. And then list what you're looking for. This is normally a derivative. Step 5, implicitly differentiate the equation with respect to time. Usually this equation will have at least 2 derivatives. If it has more than 2, we're going to have to rewrite things or find a relationship between the variables and rewrite the equation in step 3 using this relationship. We'll look at this in a couple of examples. Step 6, we're going to plug into the particular information and solve for the desired quantity. Remember, don't do this until you do step 5. You have to make sure you take a derivative first and then plug in that information. If we plugged in the information first into the expression, we usually would get just a bunch of numbers and the derivative would be 0. So we have to first find the derivative implicitly, then plug those values in. And then step 7, write down your answer and circle it with your favorite color. So let's look at an example. Again, from the worksheet, this is example 3. It says, Bugs and Daffy finish their final act on the Bugs and Daffy show by dancing off the stage with a stationary spotlight covering their every move. They start at the center of the stage, moving off the stage to the right along a straight path at the speed of 4 feet per second. The stationary spotlight is located 20 feet away from the center of the stage. What rate is the spotlight rotating angle of the spotlight beam when they are 15 feet from the center of the stage? All right, we have a lot of information to go through here. I'm going to use my computer, excuse me, and say, okay, here are Bugs and Daffy at the center of the stage. The spotlight is located in the center of the stage, 20 feet from the center. So what do we know from the given information, and what do we need to find? Well, I know that Bugs and Daffy are moving along the stage, along a path to the right, at the speed of 4 feet per second. Now, once I see those units, I realize this must be a rate of change. This must be a derivative. So I know that they're moving in that direction, but I know that that distance between the center of the stage and where they are is changing. So I'm going to call that x because it's a horizontal distance. But we know that they're moving to the right at the speed, a derivative, of 4 feet per second. So that's going to be my dx dt. It's the rate of change that they're moving in that direction. I also know that the spotlight is stationary and located 20 feet away from the stage. And I can label that with a constant 20 feet because that is not changing. It is stationary and it's not going to move from that 20-foot position. The only thing that's going to happen is that I know that the light is going to rotate. So they're asking me at what rate is the spotlight rotating, the angle of the spotlight beam, because the spotlight is being rotated to keep the beam of light as Bugs and Daffy dance off to the right. So this, we want to know as the light rotates, we want to know that angle theta, what's happening here? What's the angle there? What's happening to that? What is the rate of change of that rotation? So we need to find what is the rate of change in theta with respect to time. So next we need to write an expression that will relate what we know to what we want to find. In this case, we want to relate x to theta because we knew dx dt and we wanted d theta dt. And if you look at the diagram, it really is just like a triangle, where this was where the spotlight was, 20 feet from the stage, and this was the value of x. That was the distance between the center of the stage and where Bugs and Daffy end up on the stage. And this was the rotation of the angle theta. So again, it's really just relating, having to do with a right triangle. How can I relate x and theta? Well, of course I can use tangent. This is a right triangle, so using SOHCAHTOA, we know tangent of theta is equal to opposite over adjacent. Right, now I have a function that relates the two quantities. We take the derivative with respect to time. We use implicit differentiation to find the derivative of this expression. And next, we want to know at what rate is the spotlight rotating, or the angle of the spotlight beam, when they are 15 feet from the center of the stage, which is when x is equal to 15 feet. Well, using the Pythagorean theorem and trigonometric rules in a right triangle, the hypotenuse would be 25 feet, and the secant of the angle would be 25 over 20, or 5/4. Substituting in and solving, I get my answer. d theta dt is equal to